The rate of a chemical reaction is a measure of how fast the reaction proceeds. So it is how much reactant turns into product in a given amount of time. Usually the unit will be moles per liter times second. So how many moles per liter, or how much concentration with molarity change per second. In a reaction with a fast rate, the reactants form products quickly. In a reaction with a slow rate, it takes longer for reactants to form products. Reaction rates can be controlled if we understand the factors that influence rates of reaction. So you can just see here, this one on the left is a fast reaction. The one on the right is a slower reaction. So the green on the left there is the product, and you can see how quickly it forms and how quickly it all becomes product in the fast reaction, whereas in the slow reaction, the brown is the product, and you can see how it takes a little bit longer for that to form. Were that reaction to continue and I were to keep monitoring it, eventually, just like the fast reaction, it would all turn into product. Rate of a reaction is related to collision theory. So, all year we've talked about chemical reactions happen and these reactants form these products, but we've never actually talked about the mechanism by which that occurs. And that's what collision theory is. It tells us the mechanism by which reactions occur. So when you're doing a titration and you're adding base to acid, and the hydroxide ion is reacting with the hydrogen ion to form water. Well, how is that hydroxide ion reacting with the hydrogen ion? How are they sticking together? How are they forming water? And the answer is they are colliding. So there are three parts of collision theory. The first is very simple. In order for a reaction to occur, things have to collide. Only a small number of collisions are going to actually produce reactions. And we're going to talk about the conditions that a collision needs to have in order to produce a reaction. So the first condition is that the substances must collide in the correct orientation. So I have this carbon monoxide reacting with nitrogen dioxide to form carbon dioxide plus nitrogen monoxide. Basically, the nitrogen dioxide is just giving oxygen to the carbon monoxide, right? And so in order for that to occur, those two molecules have to collide in the correct orientation. So in A, when the two oxygens are colliding with each other, that's not the correct orientation. The molecules just bounce apart, rebound, unreacted. In B, where the oxygen from the carbon monoxide is hitting the nitrogen, again, that's the incorrect orientation. They just bounce apart unreacted. C is the correct orientation, where the carbon from the carbon monoxide is hitting the oxygen from the nitrogen dioxide. For a very, very, very brief moment, milliseconds, billionths of a second even, everything sticks together and it forms what's called the activated complex. And then the activated complex will split apart into the products. In D, we have the correct orientation, but we have it says it has insufficient energy. And that brings us to the third part of collision theory. Reacting substances must collide with sufficient energy to form an activated complex. An activated complex, also known as a transition state, is a temporary unstable arrangement of atoms where old bonds are breaking and new bonds are forming. So C here is my transition state, where the bonds between the bromines are forming and the bonds between the nitrogens and the bromines are breaking. But for a very brief minute, everything's kind of stuck together. Then it'll break apart into your products, the bromine and the two nitrogen monoxides. That amount of energy that collisions need to form the activated complex has a name. It is called the activation energy. So activation energy is the minimum amount of energy needed to form the activated complex and lead to a reaction. If your collision has more than the activation energy, you're going to have a reaction. If it has less than the activation energy, there's not going to be a reaction. And it's an all or nothing situation. The reaction happens or it doesn't. So if my activation energy is 100 kilojoules, which it's not, but let's say it is. If my collision has 99 kilojoules, no reaction. If my collision has 99.5 kilojoules, no reaction. There is no reaction unless you have the correct amount of energy, called the activation energy. If you have more than the activation energy, reaction happens, nothing extra happens, nothing special happens. It's just the reaction occurs. So all or nothing, it happens or it doesn't. A way to visualize activation energy is using one of these things. This is called an energy diagram. And so you can see the activation energy is the distance from the energy of the reactants up to the top of that hill there. That's your activation energy. So again, if I have a collision here, it's going to go back, bounce off, unreacted. It's only where you have a collision that's up here at the top of the hill that you're going to have enough energy to form that activated complex. Once it forms that activated complex, it will definitely then continue on and go down into products. This is an energy diagram for an exothermic reaction. Energy diagrams have some specific pieces that they all have in common that we're going to talk about here. So an exothermic reaction is one in which energy is released. So your products are of lower energy than your reactants. So that's why this, hill looks like this. The things that all energy diagrams have in common, we have our reactants here, we have our products there, we have our activation energy, which is the difference between the reactants and the top of that hill. We have our activated complex at the top of the hill. And then we have the overall energy change of the reaction, the difference between the products and the reactants. From thermochem, you might remember that's called delta H or enthalpy of the reaction. So all energy diagrams are going to have those 5 things. This is an endothermic one. In an endothermic reaction, energy is absorbed. So the products are going to be higher energy than the reactants, but they're still here in the same spots. Reactants on the left, products on the right. You still have that activation energy, you still have the activated complex, and you still have your delta H, your energy absorbed by the reaction. Is the difference between the reactants and the products. It doesn't have anything to do with the activation energy. It's just the difference between the reactants and the products. There's 3 factors that affect the rates of a reaction. The first of which is concentration. So the rate of a reaction will increase with increasing concentration of reactants. And this makes sense if you think about it in terms of collision theory. If I have more reactants, I'm going to have more collisions. So even if only 10% of collisions turn into products, if I have 100 collisions, I'm going to get 10 products. If I have more collisions, if I have 1,000 collisions, I'm going to get 100 products. So, the more reactants you have, the more collisions you're going to have, the faster the reaction is going to proceed. The second factor is temperature. The rate of a reaction is going to increase with increasing temperature. As temperature goes up, things have more energy, right? They have more kinetic energy, they're moving around more, they're moving faster. So as temperature goes up, the rate of my reaction is going to go up because, yes, there are going to be more collisions because things are moving around more, but more importantly, you're going to have more collisions that have enough energy to form that activated complex. You're going to have more collisions that have an energy greater than the activation energy. The third thing that can affect the rate of a reaction is a catalyst. A catalyst is going to speed up a reaction by lowering the activation energy. Lowering the activation energy speeds up the reaction for the same reason temperature does, because you're going to have more collisions that meet or exceed that activation energy because it's now a lower number. So notice in the catalyzed versus uncatalyzed pathway, a very important thing here, the reactants and the products are still at the same place. That doesn't change the overall energy of the reaction. What it does is it lowers the activation energy, and the way it does that is by providing an alternate pathway for the reaction to occur. So without a catalyst, I have to push these boulders all the way up the hill, and then they fall off. And they're only going to fall, this is a good analogy for activation energy and all that stuff, because they're only going to fall off the hill if they get all the way up to the top. This boulder right here, it's not up high enough yet, right? And so it hasn't met that activation energy. If I let go of it, it's going to roll back down the hill unreacted. If I push it to the top of that hill, though, it will go over, it will form products. With the catalyst, it just provides an alternate pathway. So maybe there's, another path over there where I can push those boulders. And so it's a lot easier to get them in that pathway because it's not as high. Notice they start at the same place, they will end at the same place at the bottom of that hill. It's just the pathway that is different and takes less energy. As a reaction proceeds, the rate of a reaction is going to slow. So the pink line here is the reaction rate, and then the blue line and the red line are just to show you this change in slope as the reaction proceeds. So initially we start out very, very fast, reactions occurring very quickly, and we have a very steep slope. And then as time goes on, we have a slower reaction, less steep slope. Why does this occur? Because as time goes on, reactants get used up. So there are fewer reactants, which means there's going to be fewer collisions between reactants, right, to form those products. And then eventually, all of your reactants get used up and you kind of level off there. So a little conceptual check. In a reaction between two gases, what would be the result of increasing the pressure? If I increase the pressure, I'm pushing those gas particles closer together. And because those particles are closer together, there's going to be more collisions. So there's going to be an increase in the reaction rate.